In this work, we are basically making a shift on the traditional paradigm for belief change, of which we have seen many instances, to consider models as input, and having ontologies, particularly description logic ontologies, as a certain motivation for focusing on what we're going to call finite representability. So, as many of you already know, in belief change, we usually have a knowledge base or some body of information that represents what we already know at a certain point. And then when we receive some kind of new information, we want to change our beliefs in a minimal way. We don't want to lose previous information if we don't need to accommodate this new piece of information. And usually, this new piece of information comes as a single formula or as a set of formulas. And what we want to do here is to change this kind of representation of the input so that we receive a model instead of just a single formula. And using this model, we want to go from a finitely representable knowledge base, for instance, a finite set of formulas or a description logic ontology, and obtain a new ontology or a finite knowledge base or a finite base, which captures this new information considering what we had before. So again, we still want to minimize the loss of information, but and in this case, this loss is measured in a sense by how many models you add or remove from the models that you accepted before. And in this particular case, while we are concerned with finite representability, we are not much concerned about the syntactical structure. So as long as the result is finitely representable, we are happy. And this is perhaps the most important constraint that we are going to, that we have in this approach. We really want to maintain the representation finite. I mean, being able to represent the resulting set of models as a finite set of formulas in some language, even though we might lose the initial syntactical structure that we had beforehand. So this is our proposal. And one of the questions that may arise, why do you need models? Why do you want models as input? Because for finite representation, you can argue that it's easier to work with computationally if you have some kind of finite representation. But why use a model as input? So in some scenarios, it might be easier to have some kind of structure, predetermined structure, where that serves as your model, where you can check certain properties, for example. And one of such scenarios is when you have, for instance, image processing. So in this motivating example, we have a certain number of devices such as fridges, ovens, and air conditioner. And a certain agent might want to know or might learn that you must not place the controller of the air conditioner over the oven. So this would be considered a negative model that should be removed from the set of possibilities, while placing the air conditioner controller over the kitchen counter is perfectly fine. So this is a model, for instance, that should be accepted by that agent. And the operations that we devised or in this work, they relate in some sense with the traditional operators, which are operations where you have formulas input. So in formula contraction, traditional contraction, the idea is that we get fewer formulas the intuition. But the corresponding operation in our case is model expansion, because the idea is that in general, when we remove formulas, you tend to accept more models. And then when you do expansion by formulas, the reasoning goes in the other direction. We have more formulas, so we tend to accept fewer models. And then we get what would be model contraction. We have a certain model that's accepted, and then we want to make it unacceptable. And then there is also revision, which is a very important operation, which acts as an expansion, but usually with some concern about maintaining consistency. And this will left us future work, because we would need to understand better what would mean to preserve or to add models as you try to remove, or which other models you might remove when you are trying to do some kind of model expansion. So in this particular presentation, and in the paper, actually, we just talk about model expansion or expansion by models and model contraction. And just to illustrate, if you have a knowledge base B, which we assume that's finitely representable, it might have a model. One of its models might be the model M, that's in red. And what we want is actually to obtain a base which represents all the other models of this knowledge base, right? So ideally, in the ideal case, we just can find a certain finite representation in terms of formulas, which will have a set of models, the remaining set of models. However, what happens is that it might be the case that there is no finite base such that the set of models of that base will correspond to the desired, the ideal set of models that you want. So what would be reasonable to do if you want to ensure that the result is finitely representable? Well, if you can't have these, perhaps you can look a few steps backwards and perhaps lose a few more models and try to get something that is finitely representable. And here we have the idea of our first operation, model contraction, where we look at the maximal subsets of the ideal set of models and select one of those and find a finite representation for it. So the idea is that since we cannot get the ideal one, we lose some models that we are not supposed to lose to ensure that the representation at the end is finite. And then this is important to note. I will present the postulates here, which are a bit different from the postulates that appear in the first part of the paper, because now we have a characterization. In the paper, we just gave some desired postulates, but after some work in the meantime between the submission and this presentation, we finally managed to get a representation, a characterization for this operation. So the first and perhaps the most important postulate is success. If we want to remove a model, that model should not be satisfy the resulting base. Inclusion, the idea that if you are removing things, it doesn't make sense in principle to add new models. So these two are quite simple and very similar to the postulates that we have for contraction by formulas. And then we have this new postulate, which we call finite retainment, which basically says that you really will only lose models if that's required for ensuring that the resulting set of models that you want to get is finitely representable by a finite set of formulas. And then we can do a similar reasoning for the other direction. We have an initial base that doesn't actually contain what the set that we need. And then we need to actually increase. Sorry, the picture is incorrect. We should look at this picture in the other way around. We want to add a new model. But when we include this new model, we might get a set of models that has no finite representation in a certain logic. Therefore, we may need to add more models than we actually planned it. And then we just want to add as few models as possible to ensure finite representability. So basically, we are going to look at the minimal finitely representable supersets of the desired set of models. And then we have some postulates which are analogous to the postulates from model contraction. So we have success, meaning that we can guarantee that the model that we are adding will be a model that satisfies the resulting base. We have persistence, indicating that we are not going to lose any models. And we also have something akin to finite retainment, which we call finite temperance, which just says that if you add any other models besides the input model, this means that this was required to maintain finite representability. And now I'm going to introduce very briefly a description logic called ALC-formula. So for those who are not familiar with them, description logics are usually fragments of clustered logic for which the entailment problem is decidable. So these logics are very important in the semantic web field, and they underpin many ontological languages that you can use to express and share knowledge. And the ALC formula is basically the standard descriptor logic ALC enriched with Boolean operators. So in ALC formula, you can write concepts, and these concepts will represent predicates. In the case of description logic, you can have unary predicates or binary predicates at most. And then in ALC formula, you can combine these predicates into formulas. You can have some basic formulas which we call assertions and concept inclusions. It will become clear why we call this last kind of formula concept inclusion. And then from these basic formulas, we can use the Boolean connectives. In this case, we just need negation and conjunction to build more complex formulas. And here are just some examples of what kind of formula we can write in this language. So for instance, we can say that a worker, everyone that's a worker is a person. So we say that if you take the union of the concepts not worker and person, we get top, which indicates the whole domain. It's interpreted as the whole domain. We can say, for instance, that it's not true that Alice is a professor and that she works at the University of Bergen. And we can also say, for instance, that Bob is not a developer and work at Google. These two things cannot be true. So we can combine these formulas using the Boolean connectives, which are not present in many of the description logics. So this is something very special about ALC formula. And okay, so we have this language, and we have that framework where we can obtain sets of models and look at the best set of models that represent the result while ensure finite representability, but we don't have yet, I have not shown you any way of constructing such result. How do we actually compute model contraction and model expansion? In propositional logic, if you have finite signature, things are actually quite easy, especially if you convert everything to Ks and Fs, because you can literally represent each model with a formula and then take conjunctions or disjunctions of these models to perform the operations. However, in ALC-formula and in many other logics, things are more complicated, because even if you have a finite signature, you can have infinitely many models which can be distinguished by formulas in that logic. So what we try to do now is to take an approach which mimics what you can do in propositional logic and transport it to ALC-formula. And this approach is based in the notion of Quasimodels. I'm not going to enter into the details of what Quasimodels are, but what's important to know is that you have only finitely many Quasimodels, and that given a knowledge base, which with ALC-formula, since you have conjunction, can be expressed as a single formula, you can represent finitely all the models which satisfy this particular formula, even if you have infinitely many. This is the main feature of this structure. And one of the components of a Quasimodel, which we use to construct the finite representation, is the formula type. So basically, a formula type would be just a subset of the formulas which compose your knowledge base and their respective negations. So for instance, if you have the formula which says that Alice is not a professor, but works at the University of Bergen, we have a subformulas that Alice is not a professor, and another subformula which says that Alice works at the University of Bergen. And then as a formula type, there are many constraints to define what a formula type actually is. Two of them that's closed by conjunction, and that's if your formula is in the formula type, its negation should not be in that same formula type. Therefore, if you want a formula type for this formula, we must include it and also include each of the components of the conjunction. And this is enough. Actually, there is no other formula that we could actually include, because there are no more subformulas, and the negations of these formulas cannot appear in this set. And in using this construction, we can build a DNF version of formulas in ALC-formula. And the proof is quite complicated, but we managed to prove that this DNF version is equivalent to the original formula. And then we can use this DNF version to construct the actual operations. So for model contraction in ALC-formula, we have a construction where we take the DNF and then remove the disjuncts using a filter function, which will remove all the disjuncts which are associated to Quasimodels from models that satisfy or that are related to the input model that you want to remove. And here is just a short example where you have that kitchen situation, and that we have a user called Peter, who is a child, for example. So we have a situation where the stove STV1315 is just a name for the stove, cannot be enabled while Peter is around. So we have a formula where we didn't know that. So we have a situation where the stove could be enabled, and then we can remove this disjunct here, which is related to a model where the stove is enabled and Peter is around. And then we get just the formula which express the models that we can keep. And for sure, there are side effects of this propositionalization, meaning that we cannot always remove just one model or just one class of model with respect to ALC-formula. We end up removing more because Quasimodels end up treating the same models, treating different models as if they were the same, given this propositionalization approach that we have used, because it will only consider the evaluations to the subformulas which describes your knowledge base. Nonetheless, we have also found characterization for contraction. We have the success postulate indicating that we are in fact able to remove the undesired models. We have also inclusion, indicating that we do not gain any other models. Then we have analogous to finite retainment, but it's just atomic retainment, because we might end up removing certain models because they give the same valuation to the subformulas of the original knowledge base. And then we have a restricted version of extensionality, exactly because of how the Quasimodels look at the models, how this space of models is partitioned according to the evaluations of the input formula. And then for expansion is much more simple. We just need to add a disjunct to correspond to the evaluations that we can take from the formula types from the Quasimodels for the input model. So basically, take the input model, take its Quasimodel, take the formula type correspond to that, and convert to a DNF. So I'm a bit short on time, so I'm just going to go to this very quickly. But the idea is that in this example is that we know that the AC controller can be in the cannot be the fridge, and that AC controller cannot be also over the stove. However, we might want to include the information that is actually okay for it to be, that it's not okay for it to be over the stove. And so we have to add that extra information, which is described by this disjunct here, which is added to our original formula. And again, we also have the corresponding postulates of success and persistency. And again, we had some analogous to finite temperance, in this case, atomic temperance, because we may end up adding more models than what we expected. And we also have atomic extensionality, meaning that if two models give the same valuation to the subformulas of your knowledge base, then the result in terms of models will be the same. And just now some concluding remarks. The idea is that we are trying to propose a new way to repair ontologies via belief change with models as inputs. And our construction is based on a propositionalization strategy for ALC-formula with a characterization via postulates. And then the main challenge is coping with the finite representability constraint, because this constrains what kind of operations we need to do. So we have to compromise, sometimes adding more models than what we wanted, sometimes removing more models than what we actually wanted. And given this, this shift in the paradigm, we have many future works in mind. For instance, extending the framework for multiple revision so that we can deal with sets of models as input, and also models which are just partially specified. we also want to check how this paradigm of using models as input relates to the paradigm of learning from interpretations, which is part of computational learning theory. You also want to try different strategies to actually constructing the operations that do not have the same shortcomings as our propositionalization-based approach. And we also want to evaluate how these syntactic constraints that you have with atomic extensionality relates, for instance, with syntactic relevance and the approach proposed by Parikh of the language splitting. And finally, and perhaps more important, we want to relate this work with what's done now in pseudo contraction, axial weakening, and gentle repairs, which are approaches where you want to revise your knowledge base, which usually is a finite set of formulas, but you allow just a partial loss of your syntactic structure. So you want to achieve a certain result, but instead of going as we would do in classical belief-based approaches of just removing or adding formulas as a whole, you allow yourself to just weaken or change a little bit this formula so that you can take the new information without much loss of previous knowledge. All right, thank you very much.